Hello everybody, and thank you for being here today for this another seminar, periodic seminar. Today we will have the honor of hosting the talk by Claudio Maia, who is talking about semi-partitioning techniques of fork join tasks using work stealing. This is, if not the first time, that we are dealing with these two paradigms in the context of real-time systems. So you have around 45 minutes to entertain us. I have to mention that in the room we have people naturally expert in the semi-partitioning techniques. So be prepared for quite a long list of questions.
Okay, so if you have any questions, please ask during the talk. It's better to explain everything ahead than to actually accumulate them. So this work is going to be officially presented next week in the UC conference that will be held here in Porto, and was a work that was done together with Patrick and my other supervisors, Luis Nogueira, which is here, and unfortunately Miguel cannot be here, but he was also part of the work. So the context for this work is in the past years we've seen the evolution from uniprocessors to multiprocessors and even many core processors, but still the scheduling problem didn't become easier. So while in the past with uniprocessors the scheduling problem, we had to be aware of when a task should execute so that we could obtain schedulability of the system. With multiprocessors, the scheduling problem increases in difficulty because not only we need to know when to execute a task, but we also need to know where a task should execute. Because now we have more cores available to execute the task, and such decisions will affect what we have in the system at a certain instant of time. There are already some scheduling approaches. There are scheduling approaches that were proposed already to tackle this issue in multiprocessors, such as the global approach, the partitioned approach, and the semi-partitioned approach. So just to clarify what kind of semi-partitioning approach we are using. So for semi-partitioning approach, what we consider is that there are a subset of tasks that are scheduled globally in the platform. There are a subset of tasks that are scheduled using a static approach. So offline we decide which tasks are going to be assigned to those cores, and these tasks cannot migrate in the platform. And then what we consider is that, considering semi-partitioning, we do task level partitioning. So if a task is allowed to migrate, it will do at the job level. At the task level of the job, right? So this is the kind of semi-partitioning that we are doing. So we do not allow jobs to migrate in between. So now with the multi-core platforms available, we can also execute parallel tasks in these platforms, so that we can take advantage of, we can maximize the performance of the platform itself. So the idea is, if we have a parallel task, then this parallel task will have a region composed of subtasks that can execute in the platform simultaneously in the same time system. So this brings higher complexity to the scheduling problem. Okay? So usually what a programmer does is that it recurs to parallel frameworks to exploit the parallelism of the application, either implicit or explicit, or even, both. Okay? And many of these frameworks, they use work stealing during runtime to take advantage of the parallelism of the application and of the parallelism exposed by the multi-core platform. So work stealing is a very simple algorithm. I will just explain a bit what is work stealing, just to provide some context to the work.
Can you also say again what is implicit and explicit?
Okay. So usually what happens is that, so the parallelism can be implicit in the sense that, so for instance, if we use a parallel for, we are not saying how the parallelism will be handled by the runtime environment. So for instance, we say, okay, we have a matrix, we have this set of operations, we don't care how these operations are performed, runtime decides. So it's kind of implicit. The programmer doesn't care about what is going on as long as the runtime parallelizes the workloads. With explicit parallelism, the programmer explicitly says what is going to be parallelized in the framework. So imagine that we have a matrix, and then you say, okay, I want this part of the matrix to be sub to execute, let's say, in these two cores, and then this other part, okay, we don't care. I mean, the runtime decides. So actually, so these runtimes usually, so you imagine that you have implicit parallelism in a parallel for, and then during runtime, the platform can actually use or be optimized by the runtime by using work stealing. So actually, the runtime deals with that. Okay, I will explain now what is work stealing, just for the context. So, work stealing is a very simple algorithm. So, it works as follows. Generally, it has a global queue, and in each core we have one worker thread with a local DQ, and whenever there is workload in the platform to execute, this workload is submitted to the global queue, and then each worker thread picks this work from the global queue, and then from that point on, the work executes, I mean, it's local to the worker thread. Whenever one core is idle, it is allowed to steal work from another core's local DQ, so that the workload is balanced through the platform. A DQ is a special type of data structure, which is actually treated as a stack. So on top of the DQ, we have operations like push and pop, and then on the other hand of the DQ, we have DQ operations. So those are the only operations that are allowed in this type of data structure. The benefits of having work stealing are that, so we can reduce task contention because we are dealing with global plus local, and then the load balancing is performed at the local level and not at the global level, so we don't have contention on the global queue. So it load balances the workload, of course, because whenever a core is idle, we go to the other core's DQ to fetch work, just to avoid having to avoid being idle. So data locality is also preserved because of the push and pop operations. We are maximizing, I mean not maximizing, but we are increasing the probability of having data in the cache. So due to that, we preserve that. I mean, but it's probabilistic, okay? Nevertheless, this approach is not ready for real-time systems, but already some algorithms were proposed that basically for priority systems that can be used in real-time systems context. However, no schedulability analysis exists for it. So this sets the context for this work. I'm not sure if you have any questions. I mean, so far this is very...
What stealing comes under implicit parallelism or explicit parallelism?
Sorry?
What stealing comes under implicit parallelism?
You can have stealing. Basically, the rule for stealing is simple. Whenever one core is idle, it chooses randomly another core in the platform. It goes there and it goes to the DQ of that core and checks if there's work to do. If there's work to do, it picks that work and starts executing that work. If there's no work to do, it will basically just generate another random number between 1 and the number of core that you have. It will check that core. So let's say, okay, the first core was number 2. It doesn't have any work. Let's generate one number between 0 and 4. Imagine that your platform has like 4 cores. Then, okay, now I generate 3. I'm going to core 3. Do I have work? Okay, if I have work, I steal. If I don't have work, I don't steal. Whenever I cover all the cores and I don't have work to do, I just basically stop waiting for another bunch of tasks arriving to the system. Okay, so with implicit and explicit parallelism, so implicit and explicit parallelism, let's say that it's at the programmer's level, okay? And then you have runtime, and work stealing only occurs during runtime, okay? So the contributions of our work, so we provide a framework that allows us to schedule fortran tasks using this semi-partitioned scheduling. We take advantage during runtime of work stealing to decrease not to decrease, but to reduce the average response time of tasks. And by decreasing this, if we manage to reduce the average response time of the task, this allows us to execute other tasks with a lower priority in the system, or even save energy consumption due to load balancing. Another interesting property of this algorithm is that, of our framework, is that as we are dealing with, let's say, as we are applying work stealing in a controlled setting, our policy can be used in real-time systems. So, our system model is composed of fortran tasks. A fortran task is basically, so here it's more formal. So, a fortran task is divided into segments. Okay. The hot segments are executed sequentially. The even segments are composed of several subtasks that can execute in parallel if the platform allows it. We also use the constraint deadline model, so the deadline can be less than or equal to the period. The processors that we consider in the platform are homogeneous, so they are identical in terms of processing capabilities. And in each core, we assume a fully preemptive DDF schedule. Okay. Concerning the assumptions, and this is one huge assumption that you need to know. We do not consider tasks with a density greater than 1. Nevertheless, we believe that we can use decomposition approaches to convert tasks with a density greater than 1 into a set of subtasks with density less than or equal to 1. As long as task structure is preserved, because we need to know the task structure ahead in order to take advantage of the work stealing during runtime. Okay. So our approach is divided into 3 phases. So we have 2 offline phases and 1 online phase. Basically, the 2 offline phases we need to take to basically check the schedulability of the task set. Okay, and once the task set is schedulable, we take advantage of the work stealing policy during runtime in the 3rd phase. So our first phase is the task assignment phase. Here the objective is to select which tasks are non-migrating and which tasks are considered as migrating tasks. So this selection is based on task density and the demand of each core after the task is assigned to that core. So what we do is that we separate sequential tasks from parallel tasks, and then within each group we separate these tasks into heavyweight tasks and lightweight tasks, being the threshold at 0.5. Okay, because of the value that we chose. So then we apply first fit decreasing to the sequential tasks, so that we increase the probability of having parallel tasks as migrating tasks, so that we can take advantage of work stealing during the 3rd phase and use it for these parallel tasks. So we cannot apply work stealing to sequential tasks, so that's why we delay the allocation of parallel tasks and then try to take advantage of work stealing during runtime. So to give you an example, here we have a set of tasks. We order them, so sequential tasks, parallel tasks, ordered by utilization. So this is a lightweight task, heavyweight, lightweight, heavyweight, just to simplify. So this task is going to be allocated in the 1st core. The other task does not fit in this core, so it goes to the 2nd core. Okay, then we have, so sequential tasks are done. Then we go to a parallel task, so it has a 0.3. We can fit it in the 1st core. Okay, we are done. Then this task cannot be actually allocated to any of the cores, so it does not fit. we consider it as a candidate migrating task. So the output of the first phase is a set of non-migrating tasks. So these tasks are allocated, they don't move, they don't migrate, statically assigned to the course. And we have a set of candidate migrating tasks. In this case, this task, which is parallel and has a 0.5 utilization. Yes.
So how do you put this 0.5 utilization in this thing?
Okay, just give me a second. Actually, this is like made up value, okay? But in this case, the utilization here, you compute. So actually, this is density, okay, not utilization. However, usually we use implicit deadline, so we consider utilization because it's the same. But actually, what you do, you sum up the execution, the worst case execution time of each subtask, okay, to get the total execution time, and then you divide that by the periods. So for instance here, because actually, so I didn't explain that. So this is a parallel task, but actually we treat parallel tasks as if they were a huge sequential task. Okay, so density and utilization are computed in the same way as you would do for a sequential task, and that's why we have this restriction of. However, that's why we have this restriction of task density not being greater than 1, because there are some parallel tasks. Regularly you can easily find parallel tasks with the utilization or the density greater than 1. But for that you need special algorithms to take care of those tasks, because then you start having tasks with utilization of 1.5 and 2, and for that you need at least a certain number of cores to actually make the task schedule. Okay? So, not sure if that answered the question.
Yeah.
Okay. So, okay. So now that we have the set of candidate migrating tasks, we move on to the next phase. And then in the next phase, the objective is to determine a pattern, an execution pattern, which allows us to schedule the task. So this task cannot be scheduled in any of the cores. So we use, in order to optimize that process, we use the multi-frame task model, which basically divides a task into frames. So, basically treats a task as if it was a multi-frame task, where each job instance is treated as a frame. And then, based on that, we try to allocate each frame of the task into a core, or a set of cores, so that we can achieve schedulability. And then the pattern repeats itself. So, for instance, here we have the same task, which has this pattern, which I will explain briefly. It has, so here is the deadline and then the period, and then this is the part that will execute in the first core, this is the part that will execute in the second core. So what we are saying here is that the first instance of the task will execute 3 time units in the first core, and it will execute the remaining instances 3 time units at a time in the second core. Okay? So this is important because we cannot allocate completely the task into the core offline. So we need to actually devise some method that allows us to execute that, and that's why we use this model for migrating tasks. So our algorithm in this phase works as follows. So for each core, we want to check the largest number of jobs that can be executed in it without violating the schedulability of the tasks that were already assigned and the current tasks that we are checking. So for that, what we do is that we chose a value ki, which is equal to the hyperperiod over the period of the task, which will basically says, okay, the number of frames that we will have for that task that we need to consider. So for each core, we start our pattern computation at this number. Of course, it will be non-schedulable, because otherwise we could allocate this task offline into the course. And then what we do is we decrease this value iteratively, 1 unit at a time, and see if we can find a pattern that is valid for that core in terms of schedule. Yes.
Just to clarify, in this case, the string that you have inside the parenthesis,
Yes.
this tuple, it will consist of either zeros for some jobs in this repeating pattern, or in this case 3 would be the total execution time of the fork join task,
No.
the sum of all its C.
So, yes, so this 3 is actually the total execution time of the task, which will execute. So imagine in this case we have 24 units of time, okay, which is the hyper period. So 24 divided by 6 will be 4, so we'll have 4 instances that will execute. Each instance, or each frame in this case, will execute every 6 time units. What we do is that, okay, so the first instance of the task will execute in the first 6 time units, okay? And then the remaining ones in the first core, which is important, and then the remaining the remaining 3 instances will execute in the second core every 6 time units. But the task executes completely. The initial multi-frame model, it's not considered, I mean, does not consider this. What's actually the initial multi-frame model, what it does consider is that it considers that tasks actually have a varying worst case execution time. So in the first instance it could execute for 1 time unit, and then in the second instance it could execute for 3, and then for 1, and then for 3, and then you find a pattern, a repeating pattern that executes every hyper period with the pattern that you just devised. But in this case we do not consider that, we consider that the task executes completely during the period.
Yes, I mean, even in this case, we could say that it is, let's say, an extreme case, because for it would be 0. Okay, it would be 0. Why? Because the task would be elsewhere. But on one processor, you model it like this.
Yeah. Yes. So actually here what we are saying is that, okay, the task will execute in another processor.
So
we don't care
every first, fifth, ninth time that the task arrives, it will go to the first processor, and all
Exactly.
other times it will go to
Exactly.
the second.
Exactly, that's the case. Actually, I have an example that would show that, but I would rather, I mean, I prefer to explain every step, every phase, and then I will show the example. So in the example it will be clear, but it's exactly that, okay? So, okay, so iteratively, continuing, iteratively we decrease the KI until we find a valid execution pattern that can be executed on that core, or no pattern exists for that core. Once we cover all cores and all migrating tasks, in the end we will have a decision saying either we have a pattern and we can execute this task in this platform, or we don't have a pattern at all and this task set is not schedulable at all. Okay? Once we find a pattern, and assuming now that we found a pattern, we move on to the online scheduling phase. So here the idea is to apply work stealing among the cores that share a copy of the task. So here, as we are treating this migrating task as multi-frame tasks, they will be executed through a set or subset of cores. So these cores, we assume that they share a copy of the task for the purpose of overhead, okay? And actually to control the number of migrations in the task. And so in this phase what we do is that, okay, we know the pattern of the task, we know in which cores the task will execute. So let's try to reduce the average response time of the task by applying work stealing to this task. Okay? So here the rules are pretty much the same as the ones that I explained initially for the standard work stealing algorithm. The only thing that changes is that we need to consider admission control and priority. So still occurs the same way, so one core is idle, it can still work. If one core is idle, it can still work from another core, as long as it shares the same migrating task. We also steal from the DQ of another core. Then here, what we do is that if 2 cores share more than one migrating task, we need to consider the priority of the task so that we don't, to avoid priority inversion. But if we have only one task, we don't need to care that. And then what we do is before stealing, we apply a mission control. Remember that this occurs during runtime, so we have to control what is going on in the platform so that we don't break the schedulability of what is already going on, already executing in the course. So this is the example. So on your left, what we have is the example why we need a multi-frame task. So for instance, in this scenario, task 1, so this is the execution time, then we have the deadline and then the period. So for instance, in this case, if we try to execute task 1 in core 1, we reach to a deadline miss, so we cannot execute the task here. And then if we try to allocate the same task, we cannot execute the task in core 2. So this example is composed of 4 tasks. So these are the densities of the tasks. And if we try to apply our phases to this task set, we allocate task 3 and 4 in the first core. We allocate task 2 in the second core. And then we cannot allocate task 1 into any of the cores, so the task 1 is selected as a migrating task. Then we move on to phase 2, and then in phase 2, we start with, we know that Ki is equal to 24/6, so it will give us 4 frames for the for task L1, and then applying the algorithm, we reach this pattern. So in the first frame, we execute the task here, okay, in the first core, and then the remaining 3. So you see here that you don't execute the task at all here, and then here you execute the remaining 3 instances in the second core, okay? So task 1 is also a parallel task. So we have 1 unit of sequential time execution, 2 units with 0.5 time units of execution, and then another sequential unit of 1 unit of time, 1 time of execution. So during runtime, we take advantage of work stealing, and we still work in the first instance because the core is idle, so we can still work here. And actually, this makes us improve the initial response time in 0.5 units of time in the first core. Okay? Then we could execute here whatever we wanted to execute, as long as we don't break the schedulability of the system. Okay? So usually we assume that we can execute tasks with lower priority. For instance, in the remaining instances of the task, so in the second instance, we try to steal, but we don't have any benefit for the platform, and then in the remaining instances, there's no possibility of stealing, so the original schedulability of the system still holds, and we don't mess up with that. Yes.
I was thinking, how do you check the utilization of the core? Because you will put the task like.
Oh, okay. Just some.
No, if
here.
If it's needed for units, like the first frame.
Okay, you are talking about multi-frame tasks, how we do schedulability.
Yeah.
Okay, I will explain that. I won't explain it in detail because the process is very complex, but I will explain it briefly. Okay, but what you actually, I guess it's here. So what we do is, in order to compute, so for the offline phase it's easy, just sum up the densities of the task. You have the capacity of the platform, you know that the capacity is 1, 100, and then you just sum the capacities until you reach 1, and then you are safe. Now, for these migrating tasks, you need to consider the pattern of execution. So you need to consider exactly what is going on in the platform at this instant. And actually what we do is that, so there are 2 options of doing that. Either you consider the worst case, so you consider that all instances will be packed in the beginning, because here you are dealing with the critical instance, because you are treating each core individually, so you can deal with the critical instance. So either you consider that all instances of the core start executing as soon as possible in order to check for the critical instance, or you can use the pattern and you use the demand bound function, saying, okay, you shift everything to the beginning of execution, and then you shift everything to the beginning, and then you check the demand at specific intervals so that you can check for the worst case. Okay, but you have to consider the pattern of execution. Okay, so it's more or less written here. So for the non-migrating tasks, it's like standard DBF or utilization-based test, so just some. For the migrating tasks, we have a modified DBF that actually considers the execution patterns of the task. Okay. For the online phase, we do admission control, and for that we compute intermediate deadlines based on the slack and stealing window. So actually, for our approach, you need to consider what we consider the fork points. So at a certain instant on time, you know that the task will fork. So you see what you have to execute during those intervals, plus the slack that you have available in the system. Then this allows us to compute an intermediate deadline. And then based on that, that deadline will be used when you will steal. So basically what you need to check when stealing is that, okay, do I have enough idle time to execute this task in my core? As long as I mean, within this interval between the fork point and the deadline. If so, I steal. If not, we don't steal. Okay? So to validate all of this, this was implemented in MATLAB. So what we actually do is that for the offline phases, it's easy, it's just the algorithms, you just implement them. For the online phase, in order to measure the gain that we obtained for the work stealing, we actually implemented a runtime scheduler that actually schedules each task until the hyper period, and then measures the benefit of that. So all tasks in our system are randomly generated. Tasks can be sequential or parallel. The number of segments that we chose, so a task can have segments between 1, 3, 5, or 7. If task has the number of segments equal to 1, then it's a sequential task. The number of subtasks that we use per task lie between k and 10, so at most we have 10 subtasks per task. And then the maximum execution time for each subtask is equal to 2, and the period is generated in the interval ci, and the number of tasks times the maximum execution time per subtask times 2. Then we generated 1,000 task sets for 2 and 4 cores respectively. What we measure here is that, what we measure is the worst case execution time, worst case response time, using a work stealing approach versus the same approach with non-work stealing. So what we actually do is, we execute the tasks during runtime using a non-work stealing approach, and then we apply a work stealing approach to the same task set, and then we see in average how much did we gain, and then we use that to show the plots that you will see. So concerning the generation profile, we have, in purple we have the total task sets that were generated. In red we have all the schedulable task sets. In blue the unschedulable task sets, and then in green a very important line, which are the discarded task sets. Discarded because our pattern procedure is combinatorial. So in order to obtain valid results in a useful amount of time, we had to choose a threshold from which we had to discard tasks, otherwise the procedure would take too much time to execute. So actually that value was chosen at 10 frames. So a multi-frame task, a migrating task cannot have more than 10 frames, otherwise the task set is discarded and we move on to another task set. In terms of results, so what we show here is the improvement in terms of average worst case response time per task in task set. So here we have the utilization of the task sets. Here we have the gain per task. So in average, we see that we gain 2% per task in a task set, and the value decreases with utilization. It actually makes sense because when you increase the utilization of the system, you are decreasing the opportunities for stealing. So that's why we don't usually at higher values of utilization, you don't have any improvement in terms of response time. So these are the results for 2 cores, and these are the results for 4 cores. The results are more or less the same, which actually we conjecture that probably that will be the case if we start increasing the number of cores in the platform, but that is something that we have to do for future work. Okay, so we have also some results. So in some cases we have results between 10 and 50%, or in 4 cores between 10 and 12%, I would say. So considering now the overheads. Cores that share a task have a local copy of the task. So this is one of the assumptions that we use, but actually this assumption is platform dependent due to memory constraints. So actually what we do, I mean, this assumption is only valid if you have enough memory on your platform, because if you try to apply this for embedded platforms with smaller amounts of memory, then you cannot use this. Or at least you will use this, but it will have a cost, because at every point, I mean, whenever you want to steal, because actually that's what is involved, you have to fetch code and data. Okay? Assuming that we have a local copy of the task, we don't have to fetch code because the code is fetched in the beginning. We just need to fetch data whenever we want to steal. But that's an overhead that will always exist. Stealing may cause interference on the shared bus. This is to say that our approach is not valid for safety critical systems or more critical systems, because whenever you steal, you have to access the bus that is shared between those 2 cores. Okay. The overhead of stealing itself is supported by the idle core. So the core is idle, steals work. If the core from which we are stealing is doing some useful computation, usually we don't need to stop the core from its execution, because we just are accessing memory. Okay. Concerning the number of data transfers, we can bound this, because for that we just need to know the number of subtasks and the number of cores that share a task, and in the worst case we know that number of subtasks will migrate to that number of cores, and that's the worst case. Okay, so this is to say that the number of migrations is bound, basically. Our online admission test, we consider that the overhead is neglectable, because we just need to know the time instance and the time instant and the available slack in the platform, and this is just a small equation, so we don't see any overhead on that. So to conclude the talk, we propose a framework for scheduling parallel tasks on multiple platforms, combining semi-partitioning and work stealing. We show that it's possible to decrease the average worst-case response time of the tasks and to bound the number of migrations. Okay? So for future work, we want to actually test the scalability of the approach by increasing the number of cores that we want to test. So instead of testing for 4, we want to test for 8, 16, or even 32. We would like to try different allocation heuristics. So for now we are just using FFT, but Patrick thinks that if we change the allocation heuristic, then we should have at least some differences, or we may have some differences in the final results. What we definitely need to do is to have a better mechanism for pattern detection, because the one that we are using is combinatorial, and actually that has been shown that is the bottleneck in our framework, because for instance, just for a simple task set with 10, with a migrating task with 10 frames, MATLAB can easily go to 6 gigabytes of memory just to compute the patterns that we can use for the migrating task. So definitely that's a feature that's a part of the framework that we want to improve. And with that, I guess that's done. So if you have questions, feel free.
So we have time for a couple of questions.
Sorry, the assumption about that the density is less vertical than one. Let's say this assumption is reversed. Will it affect the online stage of the approach?
Sorry?
The assumption that the density
Okay, we relax the assumption.
will it affect the online stage of the approach?
No, actually,
so it would
it's just
be the same.
because actually what happens now is that if you relax that assumption, you need to have a schedulability test that considers those type of tasks, and then you have to consider it during the offline phases. So actually what is missing is a schedulability test, let's say, that considers parallel tasks that are also migrating tasks, which are also multi-frame tasks. So we don't have a test for that. So as we don't have a test for that, we had to actually impose this restriction because we are using the test that was originally developed for multi-frame tasks, okay? But once we find a test for that, because actually that's what is involved, and once we find a test for that, then everything else in the approach maintains.
And in this task model, you do not allow nested forks. So it's
This is just a simple for join. However, it will be the same. The restriction here is if you have a test that says this task set is this task is schedulable in this platform, okay, nested, tag, model, or whatever, any parallel task. If you have a test for that type of task, then anything else in our scenario doesn't change. Okay.
Yes, well, it's two different questions. One is more of an observation, but I would like you to confirm. So, your schedulability test itself is not aware of the, or how to say, is orthogonal not to the work stealing. So even if whether you apply work stealing, which you do, or not, this is not being used by the schedulability test itself. It is only later that you use work stealing in order to bring down the average response time.
Exactly. Because so we use our schedulability test, both of them. So we use one schedulability test for in the first phase, so for the non-migrating tasks, okay. Then we use another schedulability test that considers what was allocated into the course in the first phase, and then considers the migrating tasks that we are dealing in the second phase, which are also multi-frame tasks as we saw. Okay, that's another schedulability test. And then online, actually, it's what we do online. It's independent of what we did offline, because online we know that the task set is schedulable. If we don't change anything, the task set is schedulable. And then if we change anything, and that can only occur if we use work stealing, okay, we need to check what we are doing. And then that's why we have this third online admission control test, just to check, okay, if I steal this work, will I mess up with something that is going on in the system? Because for instance, if you are dealing with a task that has, let's say, a higher priority, then, if you are stealing a task that has a higher priority than a task that you are executing in your system, then as that task has a higher priority and you stole that task, probably you will change some deadline in your system, and you don't want to mess up with that, because if you do that, then you will mess up with what you did offline. Okay? So in each of these phases we have its own schedulability test. So that's why I was saying to Coach that if you find a test that says this migrating task, which is also a multi-frame task, is schedulable in this platform where we already pre-allocated all of these tasks, then we are safe work stealing can occur, because work stealing is an online property of the system. And actually, to measure this, we had to simulate execution. So we could also, I mean, we could have real tasks executing, or we could simulate execution of the tasks. And then to measure these changes in the response time, what we do is actually we apply EDF to the task sets, and then without work stealing, and then we measure the values, and then we do the same applying work stealing, and then we measure the values, and then we compare both, and then we generate the plot. So actually, for instance, the amount of code for this work is like 3,000 lines more or less in MATLAB, which is a lot, because we have to simulate everything to generate these plots.
Okay. There is lots of potential to continue this work in various different directions. But one practical thing, and I mean, I'm not able to propose what this should be. Probably if you ask Paulo Souza, he will. But this, I mean, when you check other cores, I mean, you would need to have on the operating system level a data structure that is efficient without too
Sure.
much contention. Have you thought about this?
Actually, that was one of the questions of the reviewers, because we assume that we use the data structures of work stealing, because I mean, so actually work stealing is an approach that works on top of the operating system and not at the operating system level. So they don't have restrictions such as, I mean, usually because they consider the average case scenario, not scenario as we do the real-time case. But we didn't consider any special data structure. But if I start thinking about it, then actually we need to have efficient data structures, because you have to minimize the number of migrations that occur between cores, because that's what it really matters. And for that, it also depends on the architecture, because for instance, if you have two cores, because you could impose some restrictions at the core level, saying, okay, we can only steal from the cores that are actually in the same die, for instance. Because if you go and still work from other cores that are not in the same die, then the amount of time that you take fetching data from the other core, you would have to go through the bus, fetch the data, so probably it wouldn't be useful stealing in some situations.
Last question?
I can ask more questions. Okay, so when you have fork join task, I mean, there is those how to say brother threads that can execute in parallel with each other that belong to the same segment. But unless any work stealing occurs at runtime, they will be executed sequentially all on the same core. So would it be possible to combine your approach with another approach that, let's say, at the offline stage cuts in half, let's say some execute here, some execute there. This of course would change your multi-frame pattern, but have you thought of that? Or
no, actually we didn't consider, but that's part of what Patrick was somehow proposing when he mentioned that we should try different allocation rules, because that's a matter of allocation. So what you are saying is that imagine that you have a parallel task which is not, which instead of just considering the sequential execution in a core, you play with the task and then you try to find all the cases that are better than sequential execution. So you can say, okay, from the cases that I was showing, so you imagine that you have a task with 3 subtasks, you can execute 2 in one core and the other into another core, and then you try to play with that to see if you can even improve more the the worst case response time during runtime. I mean, that's possible, but that's part of another problem that I presented this year in RTSOPs, which actually is more focused during the online decomposition plus allocation plus schedulability of parallel tasks. Because actually what I'm saying is that allocation matters, but allocation is bin packing, okay? So actually what you are saying is that, okay, your approach already takes a lot of time, but let's put another extra time on top of it and see if we can improve. Of course it can be improved, but the thing is, it's always related to the amount of time that you take to actually compute all the steps. But it's possible, no, it's possible. What you are saying is completely possible, and actually it's possible because all the phases are independent. So once you reach the runtime phase, once you have state that your system is schedulable, then online is just a matter of stealing work. So it's just a matter of, okay, I'm idle, I can help other cores to execute, so I can do that. Okay? So
I think that can conclude here in the session offline. So see you in 2 weeks' time. The talk that will be given by Atla.